Okay. Now, let's talk about our technical challenge. What did we want? To store more energy, we want to increase the capacitance of our objects. So we actually want more capacitance. How do we do it? And here's the thing. So if you're an experimental physicist and you want to try to increase the capacitance, you take pretty much any object. I don't know, any non-conducting object. You put it inside the capacitor. Put any non-conductor inside, and the capacitance goes up. You're too late. Now, how does that happen? If I put in practically any, and what happens if I put a conductor in between? If I put a conductor, if I fill everything with a conductor, then this is no longer a capacitor. I'm shorting the terminals, right? So here's the interesting thing. What's the difference between conductors and non-conductors? In a non-conductor, the electrons keep attached to their nuclei, more or less, right? That's our picture. So what happens if I put a single atom into a capacitor? Now, all the atoms have a positively charged nucleus and a negatively charged electron cloud. Now, it's a very dominant cloud. Let me redraw this. So I have a positively charged nucleus and negatively charged electron cloud. Okay. The net charge of the atom is 0. But what happens when I actually put in this electric field? The nucleus will feel a force one way. It will actually try to move right. So the nucleus will go right. How about the electron cloud? It will try to go the other way. But the electron cloud is actually attracted by the nucleus, so it cannot break free. What will happen is that electron cloud will move one way. The nucleus will move the other way. What will I have as a result? I'll actually have a minus plus dipole. So when I apply an electric field to an atom, I actually get a dipole. Now, what is a non-conducting solid? In a non-conducting solid, here's what I have. I have a lot of atoms. Hopefully, they are placed regularly on a lattice. And even if they are not regular, on average, here is what happens. I have this atom turning into a dipole. It becomes minus on one side, plus on the other side. But the atom immediately to its right is also turning into a dipole. So overall, their charges cancel each other. Okay. So that happens for all the atoms. I have minus plus, but this is cancelled by minus plus, which is cancelled by minus plus, all the way to the edge. What happens at the edge though? The atoms at the edge have no cancelling atom to their right. So as a result, I will have positive charges, positive net charge density on one edge of the non-conductor, and negative because this is minus plus all the way, negative charges on the other side. So this is not super different from the conductors. In a real conductor, what did I have? I had the charges moving so much that electric field inside is 0. However, here my charges are bound. They are not free to move. So they cannot fully kill the electric field inside. But what happens is that because of these extra charges, so if I look at the system once again, here is what I see. I applied an external field E. This external field tried to penetrate my object. If I had, I don't know, 10 field lines here, not all of them were able to penetrate because there are some charges in the boundary, but not all of them are killed because the charges inside are not free to move. They are bound by the nuclei. Okay. So what happens is that E inside is smaller than E outside. All right? If E inside is smaller than E outside, what happens if I take a parallel plate capacitor and fill it with non-conducting material? For the same amount of charge, plus Q, minus Q, would I have more voltage or less voltage? Let's think about it. If, let's say, the distance is D, what's the potential difference between the two conductors? It's electric field inside times the distance D. So if E in is less than E out, capacitance, which is Q over V, delta V, which is going to be Q over E in times D, which is going to be larger than Q over E out, and D, which was my original capacitance of the capacitor with no material inside. Right. So because of dipoles and bound charges, capacitance increases. Now, how much does it increase? Well, it depends on the material. Okay, so there is a material property. If I stick in, say, silicon inside, the capacitance here will be almost 10 times the capacitance for an unfilled capacitor. And this ratio between the filled capacitance and unfilled capacitor is denoted by the letter kappa or sometimes K, and it's called the dielectric constant of the material. So it depends on which material you use. If you use silicon, this is around 10. Gallium arsenide, it's around 15, if I remember correctly. For water, this is around 80. Okay. So should you go filling up your capacitors with water? It's 80 times the capacitance. Why don't we do that? Sorry. That's right. Water, actually, if there are even a few ions in there, it becomes conducting. So we must be careful. Okay? Sticking something into your capacitor is nice, but this is good if there is no dielectric breakdown. If I even have air, okay, between my two plates, if I increase the voltage too much, what will happen? At some point, electrons will start jumping from the conductor into the air. They will ionize air molecules, and I'll see a spark between the two conductors. That's called dielectric breakdown. That's also called lightning when my capacitor is formed by the cloud and the earth. Okay? So, materials properties are very important. There are two huge buildings behind this building, right? Behind the building. There is Nanotam and there is Unam. Both of them are working on nanotechnology. One of the problems they are working on is to create materials which have high dielectric constant, so that I can actually put them inside the capacitors. But they also have very high dielectric breakdown thresholds, so they do not actually conduct electricity. So you must have a very good insulator, which also has high dielectric constant, kappa. Okay? And it turns out for some circuits, actually very fast switching circuits, silicon dielectric constant is the limiting factor. You may be very angry at your phone because it's not fast enough. Maybe it's not the engineers, the software engineer's fault. It's the fault of the material. It's the material scientist's fault. Okay? They cannot find a better material for your phone to do all these fast operations. Good. So this is quite easy. When I stick, and I'll tell you, if I use, I don't know, rubber has K or kappa of 3. I'm just making it up. If I stick it all the way inside my capacitor, I'm going to increase the capacitance by 3. Okay? That's what dielectrics are good for. So let's solve an example. What if I fill half of the capacitor with a material of dielectric constant kappa? The full area is A, the distance between the plates is d. What is the capacitance of the capacitor where only half of the volume is filled with dielectric material with dielectric constant kappa. How do I solve this? That's a great suggestion. Okay, so here's what I'll do. Because I have a conductor, a single conductor up top, I know that in a conductor the potential must be the same. So I can think of the following. Why don't I think of the system as if it's split into two systems, where now the conductors have area A over 2, and one of these capacitors is fully filled with dielectric constant kappa. The distance will be the same. Let me call the capacitance of the first one C1, the capacitance of the other one C2. So what's C1? Capacitance of a parallel plate capacitor. Epsilon 0 times area is A over 2. The distance between the plates, D. How about capacitor C2? It would be the same, except I stuck in all this material, which increased the capacitance by a factor of kappa. Okay? So what's the equivalent full capacitance? Because these are parallel, C1 plus C2, so it's going to be epsilon 0 A over 2D plus kappa epsilon 0 A over 2D, or epsilon 0 A over D 1 plus kappa divided by 2. Does it make sense? What if I do kappa? Let's check this. What happens when kappa is equal to 1? What does kappa equal to 1 mean? It means I'm not sticking anything in, right? It's the vacuum. So if I'm not sticking anything in, what should I expect the result to be? Epsilon 0 A over D. So let's check. When I say 1 plus kappa, it's 2. 2 divided by 2 is 1. So I get the same limit. Okay. So that's pretty much it. Okay. Let's do a slightly harder example. Same question. But assume that a total charge Q is on the isolated capacitor. So here is my capacitor. It's half charged, half filled. And I'm going to assume that actually I have more material here. Let me try to do this with another color. The total charge is plus Q here and minus Q here. Now comes the question. What is the force on the dielectric slab? First of all, do you think the capacitor is pulling this dielectric in, or is it trying to push it outside? Let's think about the charges. I have plus charges here, plus, 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 and minus charges here. Now, how about the bound charges? What will they look like? Because electric field is partially screened, I'm going to attract some minus charges here. They will not exactly cancel the plus charges above, but there will still be some charges there. There will also be plus bound charges below. Now, can you tell me which way do you think is the electric field pointing? Now, clearly, I expect less electric field inside and more electric field, less electric field on the right-hand side field and more electric field on the left. But electric field lines cannot just disappear. So there must be something else. There must be something else going on. If I have electric field here, those electric field must actually, it must have some fringes. More importantly, it must have some fringes, it must have some behavior of curving. So, even without thinking about the electric field, I have minus charges here, which are very close to plus charges. And there are plus charges here. These guys are going to attract my minus charges. And these guys here are going to attract those plus charges. So what do I expect physically? I expect this whole slab to be sucked in. Okay, so I expect this whole slab to be sucked in. I expect the direction of the force to be towards the inside. But clearly, because we do not actually know how to calculate these fringing fields, this is not how we're going to calculate it. Let me remind you of another formula we actually learned in Physics 101. Force is the derivative of potential energy, the negative potential energy. So here is what I'll do. I will assume that the distance here is x. Okay. Let's say the distance here is L, and in the other direction I'll also have L. I'm not showing it. So what's the total capacitance here? It will again be formed of two capacitors. They both have distance d, but this one is filled. How about the areas though? The area of the first capacitor, C1 will be epsilon 0. Its area will be L times x. The distance will be d. C2 will be epsilon 0 times kappa times L times the distance that's inside is L minus x. So what's the total potential energy? Total potential energy, does the net total charge of the system change? It cannot. This is an isolated capacitor. All the charges are on the upper or lower conductor. They are not flowing anywhere. So I have to use 1/2 Q square over C equivalent, or 1/2 Q square divided by C1 plus C2. Now I have to write all of this carefully. Epsilon 0 L over dx plus epsilon 0 L over d kappa times L minus x. Let me play around with these factors. U of x is Q square over 2 epsilon 0 L over d. 1 over x plus kappa L minus kappa x. Q square over 2 epsilon 0 L over d. 1 over kappa L plus 1 minus kappa x. Now, what's the force? Force is the derivative of the potential energy with a minus sign. So all the constants in front, I don't care. I'll just write them out. Del by del x 1 over kappa L plus 1 minus kappa x. Minus q square over 2 epsilon 0 L over d. The derivative is, this whole thing is raised to the minus 1 power. Then what's inside? The derivative of the inside is 1 minus kappa. And then I have kappa L plus 1 minus kappa x squared. So the force is apparently q square over 2 epsilon 0 L over d. 1 minus kappa divided by kappa L plus 1 minus kappa x squared. Now, I'm asking the force exactly when force for x equals halfway. Okay? Let's see. Then I'll actually have one minus kappa, and then I have kappa L plus L over 2 minus kappa L over 2 squared. Oops. F is q square over 2 epsilon 0 L over d. 1 minus kappa I'll take L square out, and now I have kappa minus kappa over 2, it's kappa over 2 plus 1 over 2 squared. Okay. So this whole thing is f q square over 2 epsilon 0 L cube over D. 1 minus kappa divided by 1 plus kappa squared. And I'm going to write 2 above. Now I must be careful. By definition, kappa is larger than 1. It's increasing the capacitance. So 1 minus kappa is less than 0. So I found this F to be negative. What does that mean? This was my increasing x direction. So I found the force to be in the negative x direction, which means it's actually pulling the slab in. So that's pulling the slab. Let's write F once again. The magnitude of F is then 2 q square over epsilon 0 L cube over D 1 minus kappa magnitude. So I'm going to write it as kappa minus 1, kappa plus 1 square. Did I reach my goal? Did I find the force? Yes. Let's check the units. I know that q square over epsilon 0 or q square over c has units of joule, right? And capacitance is epsilon 0 times A over D for a parallel plate capacitor. So basically, epsilon 0 has units of farad per meter. I can write this as coulomb square per farad. So let's check everything. I have the unit of F is coulomb square divided by epsilon 0 is farad per meter. I have meter cube divided by meter. What is the unit of kappa? If it's comparing two capacitances, I said if I increase kappa, if I put a material with kappa in, the capacitance increased by 5, by 10, it's just a number. Kappa has no units. The units of kappa is 1. So this whole thing doesn't care. So I have kappa square over farad per meter. This is going to be joule per meter, which is going to be Newton. So we've actually found the correct units. Okay? We found the correct direction. We found the correct units. So this is apparently what happens. Any questions? When you don't ask questions, I get to ask the questions. So we'll have our quiz now. I'll see you actually in 2 days.